Actually, today we were supposed to move ahead, but then in our previous class there were some students who could not understand shear force and bending moment properly. So that is why I may be repeating few things just to make you understand properly. But I hope before that you might have been gone through books to understand what is shear force and bending moment. Zarka, I hope you and others who could not understand a few things in last lecture have done some homework.
So we did.
Okay, fine. Good. Today, what we will be dealing with, maybe today's lecture will be a top on your previous lecture in order to make you more, in order to make things more understandable. Firstly, what we are actually dealing with, we will be simply dealing with beams, right? And if I ask any one of you that what is a beam, it is simply any structural member, but structural member and it is subjected to some external forces, right? Beam is simply what? It's a structural member which is subject to extra. Why do we construct a beam? Because we have an apprehension and we assume that there are some loads which are actually coming on that a structural member, and those loads will be transferred to the ground. Now that is called as a simple beam, and usually we have loads which are perpendicular to the axis, right? Let's say we have different types of beams. We have a simply supported beam. We have a cantilever, can be some, and then we have a fixed beam. Then we can have also frames, as you might have seen. This is its simple portal frame fixed at two ends. It's also called as portal frame. Then we have different types of trusses, which are actually connected by a pin joints. They can be connected at all 3 points. These are trusses, frames. This is your simply supported beam. This is your cantilever. This is your fixed beams. And we also have continuous beams, wherein there are number of spans, which you might have seen all around us, because usually the buildings that we construct in and around our vicinity, you can see that there are a number of continuous spans in a beam. Those beams are called as continuous beams. They are continuous beams. And what we need to calculate here, simply as I had said in the previous class as well, that on any structure there will be some external loading, and then we have to understand its phenomena, how it basically responds, how does a different type of beam respond. A truss behaves differently compared to the frame. It's completely different procedure. And for a fixed beam, behavior can be somewhat different from a cantilever. And a cantilever behavior is somewhat different from a simply supported beams. These are and we have other structures as well which we need to analyze. But for as of now, here we will be discussing about the simple beams. Simple beams include only simply supported and cantilevers. Okay. In our this chapter, we will be dealing only with two types of beams. One is simply supported, as already shown, simply supported beam, SSB, and a cantilever beam. And then we will be having different types of loadings, right? We'll be having different types of loadings. Primarily, we have point loads or concentrated loads, point loads, or we also call them concentrated loads. What are point loads? Simply, let's say this simply supported beam is being subjected with the point load P. It is a concentrated load at a particular point of the simply supported beam. And then we can have uniformly distributed load. We can have uniformly distributed. We can have uniformly varying load. Uniformly distributed load is simply a load which has been given on any beam, or external load has been any beam, whether that be a simply supported, that be a cantilever, which is uniformly distributed. Fine. And then we have uniformly varying load. We have uniformly varying. Now, uniformly varying like this. If we have a cantilever and the load has been uniformly varied like this, a triangular load, this is called as uniformly UVL loads. Okay, these are uniformly varying loads. This is your UDL, uniformly distributed load. Okay, and this is your point load. This is our on simply supported beam. We have a point load on first cantilever. It is actually what is UVL. It is the intensity of the load. It is the intensity of the load which is actually varying uniformly. As you can see, let's say it is A and free side is B. You can see the load has highest intensity at which point? It has highest intensity at point A, which actually decreases up to the end of the cantilever. So we will have to deal now, or we will have to draw the shear force of the bending moment diagram depending upon the type of the load. Now here, as you we will be having fixed. What do we understand by fixed beams? Fixed beams are incasted beams, or and the beams are actually monolithically constructed on their ends, called as fixed beams. Now we will basically try to understand what is the concept behind the shear force and the bending moment diagram. These fixed beams are also sometimes called as built-in encastrated or beams. Now, here what we had already sign convention, or try to understand what is the sign convention that we are actually applying here. As we have already understood that whenever a beam, let's say beam is deflected such that it is concavity is upwards. Let's say this is the center line. This is the center line of the beam, and movements are such that the beam has concavity upwards. Then it is said to be positive. And if the beam has convexity upwards, then it is said to be negative. As we have already understood this part of the section in our earlier class also, we say when our movement is such that the beam is getting bended when a load is being provided such that there is a concavity upwards, then the movement is positive. And if you have convexity upwards, then in that case, this is your convexity. and here the concavity is downwards. And in that case, you say the negative. And I have also made you understand regarding the positive shear. And I have already told you like this: beam is getting sheared off. For example, beam is getting sheared off such that it is moving downwards from the right hand and upwards from the left hand. That means the beam is going in the clockwise direction. Then it is said to be a positive shear. And if the beam is such that it is moving in the clockwise direction, then the shear force is said to be as negative shear force. It will be negative shear force. Now, the shear force, what is shear force actually? I'll make you understand with one of the example so that things can be. We have a simple cantilever and it is being loaded with some load. Let's say that load is 4,000. Okay, that load is 4,000, and it is at a distance of 2 meter from the end A. Okay, from the end A. Now what we are actually here to do with, we need to understand that here the concentrated load or the point load is being applied, and that is always understandable that it is at a very small space or small area on the beam, on the actual beam. Okay, now we know that the load which is being carried by this cantilever of intensity 4,000 Newton. Let's say this is at point C. This is as point C. Now for the actual equilibrium of this cantilever, what should this cantilever reaction? What should be the reaction of this cantilever in order to satisfy the condition of equilibrium? It is simple. If it has a load of if it has a load of 400 Newton at point C, in order to be for be the in equilibrium, then the reaction, which is actually what at point A, that should also be how much? It should also be 4,000 Newton, because only then it will be in equilibrium. Otherwise, it will not be in equilibrium, and this structure will actually structural member will actually fail. So every time whenever we are analyzing, we need to take into consideration that equilibrium should be maintained, right? For that equilibrium to maintain, you will be having certain resisting translations and movements. You will be having certain reacting forces, vertical reacting forces, or bending movements in order to be on the equilibrium side. Okay, now if you want to calculate the movement, let's say this is the movement MA at point A, how much should be the movement? Simple. At point A, due to the load, actually, what will happen? Due to load, there will be a due to load, there will be a clockwise movement because the load is coming from down and to reach it to which point? At A, because we are actually calculating movement at which point? At point A. It will go in which direction? It will go in clockwise direction. Simple. So because of this load, there will be a clockwise movement of how much? 4,000 multiplied by 2, right? It will be 4,000 multiplied by 2, that will be 8,000 Newton meter, right? And then in order to attain equilibrium, again it has to attain equilibrium. Because of this load, there had been a clockwise movement of 8,000 Newton meter on the beam. Now it has been registered to move on the side A. Now, what will side A do? It has to produce a similar movement of 8,000 in order to be in a equilibrium. In order to be in a equilibrium. Simple. Now, this movement is actually called as resisting movement. Resisting or fixing reacting movement. Okay. Now, in order to attain equilibrium, there should be a resisting movement of that much amount of magnitude as it is being provided on the right hand side of the fixed support. Only then the fixed joint will be, or the structural member will be in equilibrium. Right. Now, let's say we have chosen any point. This is again our fixed beam, and this was load 4,000. It was at a distance of 2 meter. Let's say we have chosen any random point here. Let's say that point is your, it is at a distance of 1.2 meter. Okay, we chose a random point on the cantilever, which is point D at a distance of 1.2 fixed and A. Now, at this section, there is actually a possibility of failure by shear. Right, there will be a possibility of failure by shear, because as you know that will actually deflect somewhat like this. Right, it will deflect like this. Now, if the beam material what will happen? What can happen at any point? Sharing off. Let's say this was the first part, and this is the second part of the beam. This load 4,000 Newton. Now, because of the load, what can happen? Can be a failure at point D. There can be. We're not saying that there is any failure. What will be that failure of what type? Now, this, there can be a failure also. Of the beam can get sheared off. Sheared off means what? Shearing off means, or shear force means if you have a simple watermelon, if you have a watermelon, knife on it and try to cut it, which force are you actually applying? You are applying shear, because of that shearing force, this watermelon cuts into two pieces. In yourself how the shearing off actually happens. Whenever we have any beam and it is being loaded, it is being loaded at certain point, at point this, what will happen at this very point? It will be simply at this very point, or at any point, whether it is being same point or at the another point, there will be a force which will be going downwards and a force which will be going upwards. Where did that force come? That actually comes from the force which is perpendicular to the axis of the member. We have, this is, if this is our structural uh, member, and a load has been put perpendicular to the axis of the beam. A load has been put perpendicular to the beam. In order to be it in equilibrium, it should be having equal and opposite sharing forces on either side of the point of impact. application of the load, right? That is actually called as shear force. That is sharing force. How much amount of force has been shared between the 2 points of implication of the load. Wherever you have applied the load, and it will be seen that this load can be, this load can equilibrium only and when the same amount of load is being shared at that very point or at any other point. Okay, now because of any load, let's say here on this cantilever, let's say here on this cantilever at point B. Now we say the point D. Let's name this point as D, as we have already. This has the ability to get shared off into two parts actually, right? Because of what? Because of this load, and that sharing force can be, how much will be the value sharing force? Can anybody tell me? Be the value of that sharing force at point D? That will be simply, if we have a load of 400 here, there will be a sharing force of same, that is, it can get, if this is in bottom direction, here at this very point you will be having upward direction and downward direction, that is S. And how much will be that? That will be equal to again 4000. The direction will be actually vice versa, because you will be checking at point C, if you have this force on the right hand part, if you have downward force, you will be having an upward force immediately after it. And if you are slicing it or assuming that it is getting shared off at point D, then in that case, you will be having, if this is the line on the right hand side, you will be having a bottomwards, and on the left side you will be having upward sharing force, and that upward sharing force will be of intensity similar, how much? 4000, 4000 newton. Okay, and on right hand side of this section at point D it will be downwards, and on the left side it will be upwards. Now the resultant force, which is actually acting on one of the part normal to the axis of the member, right? Resultant force, which is acting, resultant force acting on any one of the parts. Now we have two parts here. On any one of the parts normal to the axis, normal to the axis of the member is called as shear force, which is 4000, is called as, actually simply it is called as shear force. Okay, and we have assumed which one is positive and which one can be negative, that you can yourself now give the sign convention and tell me which one force and which is shear force. Now I hope you might have understood what is sharing force. the force which is normal to the axis of resultant force which is acting on one of those either of the parts called as shear force. Now here again we can also see here in this direction if you can also see the direction is this way, that is clockwise, is said to be a positive shear force, then it is said to be a positive shear force. You can here say shear force will be positive throughout the length of the beam, right? Shear force will be positive throughout the length of the beam. Now let's say if we have to understand now how will be the bending moment at different points. Let's say here again we will take point D. Now we have to understand, as we already know, maximum moment, resisting moment at point A is how much? It is 8,000 Newton per meter. But I also want to know how does it vary? How can I make the shear force diagram? As in the shear force diagram, you have already said that there will be a shearing force of, let's say, 4,000 on every point. There will be a shearing force of 4,000 on every point between A and C. Shear force will be somewhat like this in positive direction. Maximum will be 4,000 at this point, and it will be 4,000 at this point. It will be a rectangular case. You can, the variation of the shear force is same on the other side because we have a reaction. How much is the reaction? Reaction is also 4,000 in this case. The load is also 4,000. Therefore, we can say the shearing force is how much? 4,000 at any point between A and C. Now, if we have to understand what is the magnitude of bending moment. Now, as you already know that at point A, we have the maximum resisting moment and zero moment because it is free to move. It can move downwards. It can go downwards. So nothing is resisting it. Therefore, you can say point B, the shear force will be simply zero. Okay, now for instance, we have to calculate the movement at different points. For example, for the same beam, which has an intensity of 400 Newton at point C, and we need to calculate bending moment at any random point D. Again, let's say it is same 1.2 meter away from A. This is your A, this is your B, this is C, and this is already written D. And the total span up till the point load is 2 meter. Now, if I want to know what will be the moment that will be offered against the rotation, because ultimately fail, it should be in the equilibrium. I should be having the resisting moment which is equal to what? Which is equal to the moment being produced by the point load. Okay. Now, if one thing is there which I already know, that the total resisting moment is 8,000 8,000 Newton meter. It is how much? 8,000 Newton meter, which is at point A. Okay. Now, for the equilibrium of the cantilever, I should be having, it is actually the movement is being produced by what? By the beam. How much is that? 8,000. And therefore, a resisting moment MA is being provided from the fixed end, which is again equal to 8,000. And it is, as you can see, it is anti-clockwise. It is anti-clockwise. And here actually beam is providing a movement of clockwise direction. Okay, beam has provided clockwise movement of 8,000, and the fixed end has provided a resisting movement of 8,000 newton meter in order to be in equilibrium. So now if the support A is not able to provide the resisting movement, what will happen? Now the let's say we don't have enough capacity of this support to provide 8,000 newton meter movement. What will happen? Simply, it won't be in equilibrium, and therefore what will happen? It will rotate in the clockwise direction. It will go down like this. It will rotate. Equilibrium is not maintained. So in that case, what will we do? We have to basically understand that here, when we consider bending moment of any beam, that basically depends upon two things, primarily the magnitude of the beam and the position of the load. It depends upon, one is magnitude of load, and secondly it is position of load. These two things are the primary things in order to understand or draw the bending moment diagram of any member. One is the magnitude of the load, and second is the position of the load. Now, as we already know that at point A, the maximum resisting moment is 8,000. Now, for instance, we have to check the moment at point D. We have to check the moment at point D. As we know, it will be having a deflecting pattern of somewhat like this, right? And similarly, we can say that let's say this is one part of the beam up till D, and then we have another part of the beam wherein we have a point load of intensity how much? 4,000 Newton. Okay. Now we need to understand when we are actually analyzing both parts, that is AD and then DB. Sorry, it is DC is here and it is B at the end. We need to understand the part DB, the right hand part, is actually free to rotate considering this point. When we are considering this point and we say the point free to rotate about D, load on the part DB will cause this part DB to rotate. In which direction? Direction. It will cause it to move in clockwise direction about D. Now we can find that there is a clockwise movement of what? There is a clockwise movement of how much? It will be certainly 4,000. It will be 4,000 multiplied by 2. One, this comes out to be 0.8. This portion is 0.8. You can say there is a movement of how much? There, because of this load, there will be a movement on point D of intensity how much? 4,000 multiplied by 0.8. That will be equal to how much? 3,200 Newton meter. That is at point D. Similarly, we can see here that the part DB has a 4,000 Newton meter, and that load is providing a movement of 3,200 Newton meter clockwise. Similarly, there will be an anti-clockwise movement of how much? Again, 3,200 Newton meter. there will be 200 Newton meter. Therefore, you can say at point D, we have a equilibrium which is has a magnitude of bending moment as 3200 Newton meter above D. Okay. Now, if we have to discuss the part AD with regard to which part? This was with regard to when we considered D and B. Now, if we consider A and D, now if I consider A and D, now in that case, what is the total movement that is actually on part D? AD is this is your A and this is D. And now, because of this movement and a reaction, we have two things. At point A, we have a movement and we have what? And we have a span of 1.2. Now we have the following movements at point AD, which is how much? Firstly, we will be having a movement of 4000 multiplied by 1.2, that will be 4800 Newton meter, which is what? I'm talking about vertical reaction. How much is that? It is 4000. And how much is movement at A? It is already calculated 8000. Now I want to see what actually happens at point D. I have two loads. One is your movement. Movement will go in which direction? Movement will go in clockwise. Therefore, you can say it is clockwise. And then I have another movement of 8000, which goes in which direction? It goes in anti-clockwise direction. Therefore, subtracting 48 minus 8000, that gives me 8000 minus, which is anti-clockwise. It is anti-clockwise minus 48 clockwise. That gives me 3200 again, Newton meter. Therefore, when I considered part of the beam, left hand side of the beam, I calculated what will be the moment at point D, and which comes out to be 3200. And I also calculated the movements when I consider part DB. These are the two assumptions wherein I can say that it is same on any of the calculation, whether you calculated the right part of the beam or you calculated the left part of the beam. When you calculated left part of the beam, you consider the external loads only, and when you consider the left part of the beam, which was AD, there you had two different things. One was resisting movement and the another was reaction, and that came out to be 3200 again. This is called actually as sagging movement. This is called as sagging movement, and here it will be called as hogging movement, which is negative hogging movement. Sign is negative in hogging and sign is positive as per the convention that we have so far. Now, let's say, I guess you will be able to do now certain and check what will be the shear force or the bending moment at various points. Let me firstly let's say we have a cantilever, simple cantilever, and it is being loaded at three, three different points. One is 1500 Newton point, we have 800 Newton at another point, and then we have one more, which is how much? 700 Newton at another point. Okay, this is the beam, and they are at a distance of 2 meter. For example, first one is 2 meter. A, B, C, and D. This is, let's say, 1.5 meter. This again is meter. Firstly, unknowns, they will be simply what? First one version, and how much will be that? VA will be simply how much? 1500 plus 800 plus 700. This is the shearing force that will be at point A. So VA will be simply equal to 3000. Am I right? Is it 3000? Yes. This will be the reaction at point A. Now, if I have to calculate the moment, if I have to calculate the moment, resisting moment, there will be a moment due to the load on the beam, but that will be resisted by the resisting moment. Let's say that is MA. And we can simply calculate that MA as MA will be firstly equal to 1500 multiplied by 2 plus 800 multiplied by 3.5 plus 700 multiplied by 235, and that will be equal to how much? Calculate it quickly and tell me how much will be the movement at point A. Give me the value MA. Your MA will be equal to 3500 Newton meter. Okay, now this movement is actually due to loads. Due to loads. That means this is this movement actually. Due to loads, there is a movement of clockwise direction. It is actually clockwise direction of magnitude 3500 Newton meter. But in order to attain the equilibrium, this fixed end should provide us with a anti-clockwise movement of it should provide anti-clockwise movement of 3500 in order to be in equilibrium. Okay. Sorry, it is 9300. Nobody is calculating, huh? Sahil, have you calculated how much is the movement at point resisting movement at point A?
So I was calculating and then
Sir, it's 9,300.
Huh, but you take so much of time to do these simple calculations. Okay, fine. This is actually the anti-clockwise movement being provided by the fixed end at point A because of the 3-point loads at 3 different distances. Now, if I have to force at any section, let's say one of the let's do it here. Let's say at point this F. Uh, I want to know what is the shear force at point F. What will be the shear force at point F without calculation? Talking about the right hand side of F. I'm talking about the right hand side of F. How much will be the intensity of shear force?
700.
Simple. It will be 700 because on the extreme end at point E, let's say at point E, we have 700 load coming in, and there will be a shearing force of 700. Simple, nothing to do much. Now, if I want to know what will be the total force on the left hand side of F. Now I want to know what will be the total force on the left hand side of F. How much will be that? Can anybody tell me? It will be simple. It will be firstly, what is your shear force on left part of F? It will be firstly you have a reaction of how much? 3000. Okay, that is going from bottom towards up. that is in this direction, that means it is positive, and there is this load coming on from the upwards, that is 1500, and then we have that comes out to be again 700, right? Again, this 700, this has to be 700 to maintain an equilibrium. On this very part, on the right hand side there is a shearing force of 700, and on the left hand side there is also a shearing force of 700. So whether you calculate to the right of any section or to the left of any section, the values won't change, because equilibrium has to be maintained at every point. We have to see what happens with the bending moment at point, let's say F. Now what is actually bending moment? It is what we called as, it is algebraic sum of what? Of forces, movement forces and reactions on either side of section, on either side of section. We actually add the movement of forces and react with calculating the bending moment. What are the forces and what will be the movement of those forces, and what is the reaction? We also include the reaction part in it, and we calculate the bending moment on either side of any part, which is actually point, it will be same, that is on one side it will be a clockwise movement of whatever magnitude, and on the left hand side of that point there it will be a anti-clockwise movement of same magnitude, right? Now if I talk about this, what we called as shear force on right hand side, this is just an example. If I want to calculate the shear force on right hand side, sorry, bending moment at F. Firstly, I will include what? I'd include right hand part. I'll include right hand part. That will be simply bending moment will be how much there is this load of 700, but it is in negative because it is hogging. It is hogging. Load will be multiplied by 0.8. It will be 500 minus 560 Newton meter hogging bending moment. It will be hogging bending moment. If I have to calculate the movement on the left part at point A, this is your movement, bending moment at F. When you calculated left, right hand part. When we calculate now bending moment at again F, but we consider left hand part. Which part? This one part. A to F. We consider the part A to F. In that case, we have to calculate the movement now. Firstly, what are the forces and the reactions? Firstly, we have a reaction. We have a reaction of how much? 3000 multiplied by how much is the distance? 2 and 1.5. F point is at a distance of 0.7. This 0.7. This is 7 is the distance, because we need to calculate it from point A. This is 0.8. Mentioned it earlier. The total distance between E is 1.5, but the point F has been located at zero point 0.7 from the D and at zero point 0.8 from the E. So in order to calculate the point, this will be again in clockwise direction. That means it will be positive multiplied by the total distance. How much is that? That will be 2 plus 1.5 plus 0 0.7. Okay, and then there will be a anti-clockwise movement of, that means it will be positive, no, it will be negative. Clockwise is positive here, so it will be 1500 into how much is the distance left. That means it will be 1.5 plus 0 0.7. 0.7. Then again we have one more movement, and that is how much? This was 1500, and then we have 800 into 0 0.7. Calculate the value bending moment at point F. Calculate it quickly. How much is the bending moment at point F?
Thousand seven hundred forty-eight 740.
Louder.
8740. 8740.
8740. There will be one more thing to be.
15340.
There is one more thing. One more thing in this bending moment at point F. Can you tell me what is that? There is one thing missing. What is that? There is one thing missing while we are calculating movement between A and D. A and F, sorry. What is it? Can anybody tell me? There is one thing missing. Quickly tell me what is it? Sahil, are you able to understand or get there what is missing in this equation here in order to calculate the bending moment towards the left of F? Now you have, listen, you have already calculated what? Values of reaction. You have reaction, this load, right? All three of them are included. But you have not, right? ME. How much was the value of ME?
9300.
Yeah, it was 9,300. Calculate the value of bending moment towards the left of F.
It will be a negative value.
Huh?
It will be negative
Yes,
value, I think.
560. Negative
How much?
560.
Negative 560. To be similar to what you have calculated here. because on either side of the bending moment there will be equal and opposite bending moment. There won't be two different values, there will be two same values. Hogging moment, here we are talking about only movement. Therefore you can say movement at every point in any cantilever is negative. At every point is negative because of any type of load on it. Okay, now if you have different types of loading here for this value, for example, if we have to draw the shear force again, it will be simply in the positive direction. Let's say at point E, if we have to draw the shear force diagram at point E, this is point E, there will be how much? 700. Then at point D, 700 plus 100, how much is that? That will be 1500. 1500. Then it go up to point, another point where we have a 1500 load. That means it is 3000 here. Point VA, how much is that? 3000. This will be your shear force diagram. All are in positive direction. Shear force. You have to calculate your bending moment diagram now. Let's make
सर ये
it.
डायग्राम नहीं आती समझ में लास्ट
हाँ?
टाइम भी ये डायग्राम नहीं आती समझ में लास्ट टाइम भी नहीं
Diagram नहीं समझ आई. I'll make you understand one more time.
थोड़ा सा अगर आप एक्सप्लेन करेंगे
देखिए, at point A, how much is the shearing force? Force. Can anybody tell me? How much is the reaction? Reaction is shearing force. Shear force. It is actually the load perpendicular to the axis. Now at point A, we have which load? Which because of the, you should keep in mind that shear force is simple load at any point. Points do we have? We have point A. We have only up till point A, B, C, and D. Now, let's say here A, we had which load? A reacting load. It's fixed at that point, we have reacting load. And how much is that? You have calculated VA. It is simply 3000. Already and earlier at every between A and between this span, between this portion and this portion, if I have a reaction of 3 at point, at the end of the point, let's say this is O, towards the left of it, we will be having a sharing force of which is 3000. That means this point B, we will be having how much? We will be having a upward move. अब अगर आपके पास फॉर एग्जांपल आपने किसी चीज पे अपवर्ड लोड डाल दिया, आपने किसी चीज पे अपवर्ड लोड डाल दिया से 1 किलो न्यूटन का, और कितना 0.5 किलो न्यूटन का वहां से आ गया. What will be the resultant? Resultant will be 0.5 kilonewton now. Okay. Similarly, up till point A and B, we had a sharing force 3000. We had a sharing force of how much? 3000. जो कि किसकी वजह से था? Because of vertical reaction. Now that down force at point B of intensity 1500 minus 50, that comes out to be 1500. Now this 1500 sharing force up till left side of the point C, and on the right hand side of the point C, it will again go because we have a load of 800 newton. Therefore, it will again go 1500 minus 800. That will again go to 700. When you have 700 from the right hand side of C, similarly up till the point of D, which is again 700. This is your positive shear force diagram. Is it clear now?
Yes, sir.
Sahil, is it clear now?
Yes, sir. Thank you.
Okay. We were talking about this, what we called as bending moment now. Are already knowing that the point is in negative form. That means it is negative form, means it is hogging. It is hogging at. Therefore, simply draw its bending moment diagram. Now let's say this is the axis. Let's say this is our axis where we can draw the bending moment at any point. Now, for example, at point E, this is a point D. We have, let's say, this is our point O, and this is our point A. Now I have to draw the shear force diagram, sorry, bending moment diagram for the same cantilever. Now, when you have calculated the moment at point E, what was the moment at point E? It will be 0 because here it is the end point. And at end point, we will be having a 0 shear force. We will be having a 0 shear force. Now, the point from where we have a load of 700 Newton at a distance of, that is point D, it is negative. Negative is downwards. Positive, if it would have been positive, I would have drawn the bending moment in the positive upward direction. Now that it is in downward direction, I'll go in negative. This is your negative portion. Let me your shear force diagram. At point E is 0, and at point, one more point where we have a load of how much? 700, and then the distance was 1.5. 700 into 1.5, here you have a movement of how much? 700 into 1.5 is 1050, right? And then we have another point, which is, this was at point 800. Then we have another load of 1500. And we also know that at this point, at point A, there is a movement of how much? 9300. Therefore, this will go up till the movement of 9300. We know already that. But we want to calculate it while coming from E to A, while coming from this direction. At point this, at point where we have a load of, how much was the load? 1500, sorry. A O, this is your, let's say this is B and this is E. And now I have to calculate the moment at point D. Moment at D will be calculated as, firstly we have 700 multiplied by distance. How much is distance? Distance is 1.5, 1.5, that is 3. Okay. And plus we have a moment of 800 into, it is in downward direction, 800 into 1.5. This is your movement at point D. Then calculate the values. Then we have movement at point A. That can be calculated 700 multiplied by, how much is the total distance? 2 plus 3, 5. Then plus 800 into, how much is the distance? 2 plus 1.5 is 3.5. And then we have one more load, that is 1500 into 2. Give me the values at MA and MD quickly. Here actually the values of these point loads will be in negative direction, negative, negative, all of them will be negatives. This will be negative here, this will be negative, negative. Why negative? Because they are hogging. Calculate the values.
So MD will be 3,300
Okay,
and MA will be 9,300. Negative both.
9,300 Newton meter, and MD will be,
3,300 minus
how much is
3,000.
MD?
Minus 3,300.
3,300. Okay, fine. 3,300, and finally it is 9,300. These are your three values at three different points. This is the bending moment at three different points. This is how you can do it at different points. Maybe I will more time with this only. These, but say you should work on this, getting understanding it properly. Shear force and bending moment diagram. I'll spend some more time on this in our next class. This is enough for today. Okay, Sahil. Today we are winding up now. Please record your attendance. Did you record the attendance?